Hello everyone, and welcome to the first international workshop on streaming analytics for process mining. So as people are gradually joining us, welcome everyone. We are just making a very short introduction about the workshop, which we hoped initially to be in Padua. So good morning, afternoon, evening, night, according to the time zones. So the organization of SA4PM, I was very happy to co-organize it with Andrea Boratin from the Technical University of Denmark, Thomas Seidel from LMU Munich, Sebastian van Zelst from Fraunhofer Institute of Applied Information Technology, and RWTH Aachen University. So what is the focus of SA4PM? Initially, we wanted to bring the techniques that are well established in the area of streaming data mining. For instance, online clustering, online classification, online sequential pattern mining, concept drift detection, efficient mining, storage and time-wise, and all the other topics related to this area, well researched in the previous 20 to 25 years. And to the field of process mining, where we have the basic initial process mining questions like, or tasks like process discovery, conformance checking, model enhancement, but also compliance checking, log file feature selection, trace clustering, model-based concept drift, and the like. So all of these two on the left-hand side are already available techniques, well-established one, and on the right-hand side, also well-established process mining tasks in the offline setting. There is an opportunity, we thought initially, to benefit from both areas, and mainly by initially starting from the techniques that are there in stream data mining and see how we can benefit from those in bringing offline process mining tasks to the online setting, but also learn from what we have already in process mining. How can we do things in a sequential way, get accurate results in parallel setting, and get back to the streaming setting. So this was the scope and is the scope of the workshop. So this is our program. We are very, very happy to have a very rich program. We will start with a keynote talk from Albert Bifet, followed by a break, and then we will have a first session where we will have two technical papers. The first is online anomaly detection using statistical leverage for streaming process events, and the second one will be on concept drift detection on streaming data with dynamic outlier aggregation. In the second session, we will have two papers also. The first is online trace ordering for structural overviews, and the second is performance skyline on inferring process performance models from interval events. So the following will be the keynote talk from Albert Bifet. So it is really my pleasure to have Albert Bifet as a keynote speaker for our version of SA4PM today. Albert is a leading researcher in the field of data stream mining. He's currently a professor at the University of Waikato and the Institute of Polytechnique de Paris. Previously, he worked at Huawei Noir Arc Lab in Hong Kong, Yahoo Lab in Barcelona, and UPC Barcelona Tech. He is the co-author of a book on machine learning from data streams published at MIT Press. He is one of the leaders of SAMOA, Scikit Multiflow, and APACHE SAMOA software environments for implementing algorithms and running experiments for online learning from evolving data streams. He was serving as co-chair for the industrial track at MDM 2016, PKDD 2015, and as co-chair of KDD Big Mine from 2012 to 2019, and as ACM SEAC data stream track from 2012 to 2019. It is great. It is really, really great to have him joining us from New Zealand, where the time zone there is 11 p.m. now. So thank you very much, Albert, for joining us, and please, stage is yours.
Thanks, Marwan. Thanks for the introduction. Yes, let me share my screen. So, yeah, thanks for the invitation. Yeah, I'm very happy today to talk about adaptive machine learning for data streams. So what I'm going to do is I'm going to first try to explain a little bit what's machine learning for data streams, see what are some of our recent works on the topic, and then see also what are the open source tools that can be used for doing this machine learning. So just to start, I think that adaptive machine learning is a topic that is becoming quite popular right now because, as you can imagine, during the pandemic, yeah, all things change. So all the things that, all the machine learning models that we already had, all the things that were already working, everything changed. And then, being able to adapt was really, really an important thing. So this is why this adaptive machine learning is really much more relevant nowadays due to that, due to these changes on the data. So what's the standard approach in machine learning? So usually the idea is that we have all the data set in one place that could be stored in memory or in disk. And then we suppose that all the data is static. And then what we do is that we build the model. And then from this model, we use this to make predictions. So what's the limitations of this is that first we are supposing that we have all the data. And then the second limitation is that we are supposing that all the data is static, that there is no change on the data. So what happens usually in many applications or in many environments where machine learning is deployed is that the people, what they do is that they train models periodically. So the idea is that, so we can train one model every week, for example, and then we use the data from every, I don't know, from the previous year. So this is a good approach, but has two main problems. One is the two parameters. So first, how often should we train? And how much data should we use? Should we train it every week? Should we use the data from 2 weeks, from 1 year? And usually the answer to these questions depends on the scale of change of the data. So imagine that the data is changing every day. Then if we train the model every week, that's not going to work. Or if we train the model every hour, that's not going to work. And then, depending on the change, how much data do we need? This is something that is something that is not fixed and also depends on the circumstances. So the nice thing of this adaptive learning approach or this data stream approach is that we have the benefits of, first, we don't need to store the data. So what we do is that we update our model continuously. And we don't need to suppose that the data is static. So data may be changing and our models are going to be adaptive. So this is a big improvement, especially in terms of that we see data only once. So we do only one pass and then we don't need to store the data. So this is the advantages of this data stream approach is that the models are going to be adaptive. So once, imagine that we have a decision tree. So we built a decision tree with several branches. We update the model, nothing is changing. But then in a certain moment, we see that the data is changing. So we need to change the branches of the tree. We need to really change the tree. So a decision tree that is adaptive is going to be able to do that. So we don't need to decide what's the right scale for doing this adaptation. So yeah, this is why this data stream mining setting is quite interesting. So the idea is that we want to be very efficient in terms of resources, so especially in time and memory. So we really want to be efficient. As you can see, we do only one pass over the data, so we don't need to store the data. So the data, so the memory that we're going to use is already fixed. So we don't need to store all the data. And so also in terms of time, we need to be efficient. And finally, we need to be adaptive. So as I said before, if data is changing, our model should be adaptive and be able to adapt to the changes on the stream. So one of the main problems when we deal with data streams is that sometimes we would like to find exact solutions that are much more efficient, but sometimes this is not possible. And then in these cases, we will be happy to have approximate solutions. So that means that we're going to have solutions with a small error epsilon with high probability 1 minus delta. So the main idea here is that if computing the exact solution is going to take days, if we can compute something in seconds that is approximate, we are going to be happy. So this is something that is very used in data stream mining, in machine learning for data streams. So let me introduce a little bit some of the methods for classification in machine learning for data streams. So remember that in classification, what we want is to build a classifier that is able to predict what are the classes, the labels of the examples. The idea is that we are going to be learning from previous data. So this is why this is called supervised learning. And from there, once we have the model, we'll be able to make a prediction with the prediction of the classes of new instances. So just some of the basic classifiers. So one interesting thing is that there are some classifiers that are already incremental, that are already streaming, and other methods that they are not incremental, and then we need to look for a streaming version. So for example, the Naïve Bayes, as you may know, the Naïve Bayes is a very simple classifier that is based on using the Bayes theorem. So basically what it does is that it computes the probability for each class. So given an instance, it's going to look at the probability for each class, and then it's going to take the class where the probability is the higher. So how we compute these probabilities? So yeah, to compute these probabilities, we use the Bayes theorem. And an important thing is that we are going to suppose that the probabilities of observing each feature are independent. And this allows us to compute the probabilities multiplying the probabilities of each feature. So as you can see, this is a very simple classifier. The only thing that we need is to compute these probabilities, and to compute these probabilities, we need to use counters. So basically, in discrete attributes, what we are going to do is that we are going to be computing counts for each class, for each attribute, or for each value. So as we only need to update these counts, then this is a method that is really incremental. So we only update the counts, and the probabilities are going to be updated once we compute them. So as you see, this is very, very simple classifier that is already incremental, so we can use it in streaming, so we don't need to do anything. The perceptron. The perceptron is another simple classifier that is very popular because it's used in deep learning when we build neural networks. As you remember, perceptron is basically maintains a set of weights, and then every time a new instance arrives, we update this set of weights, and the criteria is to minimize the mean square error. So yeah, we use stochastic gradient descent to compute this. So usually in the standard setting, what we do is that we do many passes over the data. So we do many updates. So we get a good solution. So in the case that we want to use streaming, yeah, we don't need to do anything. So we use the Perceptron algorithm as it is, and we do only one pass over the data. So doing this, we don't need to store the data. We look at the data, we update the weights, and then we get our final classifier. Another method that is quite popular is the decision tree. As you may know, the decision tree is very popular first because it's interpretable. It's very easy to understand how the decisions are made. And the second reason is because when combined in ensemble with many, ensemble of many decision trees, the resulting classifier is quite powerful. So especially we have methods as random forest, XGBoost that are quite good. So one of the things is that the decision tree is not a streaming method. Why? Well, basically because when we need to decide if we split an attribute, we need to look at data that is in memory. So yeah, this is why the standard decision tree is not a streaming method, because it requires to use the data that is stored in memory for making the splits. So how we can make a decision tree that is streaming? Well, remember, the only thing that we need is that we don't need to store the data. So what we need to do is every time we want to split, instead of looking at data that is stored in memory, what we are going to do is that we are going to wait to new instances to arrive. So yeah, so that's very simple. So instead of storing, we wait to new instances to arrive. So now the problem is, how many instances do we need? And for this, we use the HOEFFDING bound to compute how many instances do we need. And this is why this streaming decision tree is called HOEFFDING tree. So this is a method that also is called a very fast decision tree. And it's a method that if we have enough instances, we are going to have the same decision tree that built with the standard techniques. So how it works? So basically, once we want to do a split, we're going to look at the difference between the information gain of the two best attributes, and we are going to see if this is higher than a certain threshold computed using the HOEFFDING bound. So yeah, this is quite simple. And as I said, this is very fast, and this is why this method is called very fast decision tree. But this method is not adaptive. So this method is supposing that all the data is static, and then yeah, it builds the tree without adapting to the changes on the stream. So to see adaptive methods, let me talk about concept drift, how we can detect concept drift. So remember concept drift, basically we have a sequence of data and we want to raise an alarm when we see that there is a change on this, on the distribution of that is producing this sequence. And basically we're going to have two outputs. One is that we are going to have an alarm that is going to indicate us that there is a change. And also we are going to have estimation of the next value of the sequence that we're going to use to detect if there is change or not. So yeah, that's the main idea. If we want to model what's a change detector, we can model it basically with an estimator and a change detector. So this is the most simple one. So we have an input value. We are going to, from this, we're going to have an estimator that is going to estimate what's going to be the next value. And we're going to have a change detector that is going to look at if there is change on this data. A way to improve this is to add some memory. So we can add some memory that can be used from the estimator and from the change detector. And this is going to improve the change detection method. One important thing when we are detecting change is that there is always a trade-off between being fast in detecting changes and having false positives. So why is that? Well, the idea is that if we detect faster, we are going to do more mistakes. And then, yeah, this is why it's always good to look at the two measures and always try to find the best trade-off on combining two methods. So we want to be fast, but also at the same time, we don't want to do mistakes. So we don't want to have false positives. So yeah, let me mention some of the most simple change detectors. So in this case, this is the cumulative sum. So the idea is very simple. So what we do is that we cumulate the sum. So what we do is that we sum, in this case, the difference between the estimation and the true value. So we cumulate, and then once this sum is higher than a certain threshold, we detect an alarm. So we have another parameter just to smooth it. So instead of adding only this, let's say error, what we are going to do is that we are going to add this error minus this V parameter. And when we've got negative values, if the sum is negative, what we are going to do is that we are going to take a 0 as the value. So we are not going to have negative values. So this is why we have this max value here. So this is very simple. As you see, we only need to keep one variable. But the main problem is that we need an expert users to decide what are the values of these two parameters. In this case, of this threshold and this drift speed V. Another method that is really very, very similar and gets maybe better results than this cumulative sum, this sum, is this Page-Hinckley test. So basically the idea is the same. We are going to be accumulating this difference between the estimation and the input value minus this drift speed parameter V. But the difference is going to be how we handle negative value. So instead of taking the maximum with 0, instead of taking 0, we are going to be able to take negative values. And then when instead of looking at the difference between the sum and this certain threshold, what we are going to do is that we are going to look at the difference from this minimum value that is negative until until detect if this is higher than this certain threshold. So this is, again, this is a method that is quite good, but it depends also on the values of the parameters. Another method that is quite used and has advantage that there is no need of parameters is this statistical process control, DDM, from the group of Joao Gama. So the idea is that this is applied already to the classification setting. The idea is that once we learn a model, at the beginning, the error is high. Once we have more data, the error is going to go down, down, down until it gets stable, let's say to a minimum value. And if nothing changes, so this error rate is going to be low and constant. But if something changes, then the error is going to grow up. So what we do is that we look at this minimum value, then we usually look at 3 times the standard deviation to detect that there is change. And at 2 times the standard deviation, we detect that there is a warning. So this is quite useful because once we detect that there is a warning, we start or creating a new classifier that we are going to replace when we detect change, or we can store the data in a new window and we are going to use this to create a new classifier. Yes, so this is a method that is quite good in the sense that, there is no need to have parameters, but has this assumption that the data is going to be following this normal distribution. And this is why we can apply this idea of 2 times, 3 times the standard deviation that is based on this idea of 6 sigma that is used in the statistical process control. So now that we have seen some concept drift detectors, some change detectors, now let's look at how we can use them in machine learning algorithms. So Yeah, remember that we have this BFDT, this housing tree that was not adaptive. So we have this first, let's say, decision tree that was able to handle drift, that was called concept adapting BFDT, CBFDT, that was presented by the same group of Pedro Domingos. The idea was basically to keep the decision tree consistent with the sliding window. And then, yeah, from this sliding window, the idea was to change the tree so it always corresponds to this sliding window. And yeah, internally, the idea was to replace branches so that always the tree was consistent with this sliding window. So what was the problem of this decision tree? Well, the main problem was the size of the window. So how we decide the size of the window, because if the data is changing, I don't know, imagine the data is changing every day, we cannot have a sliding window of 1 week. No, that doesn't make sense. Or if the data changes every week, that doesn't make sense to have a sliding window of 1 day. So yeah, that maybe was the main problem of this tree, is that there was need to decide the parameters. And again, for doing this, we needed an expert users that, depending on the data, should be able to select what were the best parameters. So yeah, this is why there is this housing adaptive tree. This is a work that we presented in 2009. That the idea was to have a adaptive housing tree that didn't need parameters, so that basically it could decide how to do the changes without having the need of expert users that needed to decide the scale of the change and the parameters. So how would this work? So in this case, this is a housing tree that has these change detectors on each node. And then once there is change is detected, a new branch is created. So if this new branch is much more accurate than the old one, then this new one will replace the old branch. So this is the way to manage this. So to do this without needing parameters, we use ADWIN. That this is a change detector that is based on the idea of using an adaptive size sliding window. So yeah, basically ADWIN, what it's doing is that it's storing in a sliding window the data that is arriving. If there is no change, the sliding window is going to grow. But if there is change, then the sliding window is going to reduce its size only to keep consistent with the current distribution of the data. So as you see, it's completely adaptive, and there's no need of parameters. So how it works? So basically, it divides the sliding window into two possible adjacent sub-windows. And it looks at all the differences between the averages between these two sub-windows. And if looks at the difference is higher than a certain threshold, then it removes the oldest element in the adaptive window. So this is the way that if there is no change, there's no going to be any item removed. But if there is change, then yeah, the items are going to disappear due to this. So yeah, the nice thing of ADWIN is that has some of the properties of an optimal change detector and predictor. So is that is high accurate, is fast detecting change, but also at the same time has a low false positives and false negatives. So this is really important. Remember that we say that there is this trade-off between detecting change very fast and having a low number of errors. No? In this case, false positives and false negatives. And also, as it was using a sliding window, it's also good in terms of computational cost, in terms of using minimum space and time, because it's using logarithmic space. And again, Nice thing of ADWIN is that there are theoretical guarantees, so that this is something can be extended to the machine learning methods, and there is no need of parameters. So yeah, the main theoretical guarantees is that there is a guarantee on the false positive rate and on the false negative rate. So this is something that is quite useful because we know that this is limited to this probability delta. This is something that we have, and as I said before, we can extend this to the machine learning algorithms, for example, the housing adaptive tree, and this is quite nice. So we have been using ADWIN for many methods. We started with Naïve Bayes, but also with this housing adaptive tree that I mentioned before. Then also we applied this to ADWIN, leveraging bagging, also stacking. We applied this to multi-level classification, adaptive nearest neighbors, random forest, but also we applied this to frequent pattern mining, and especially in closed tree mining and in closed graph mining. So let me talk about the most recent works. So we had this adaptive random forest that was presented in 2017 in Machine Learning Journal and at ECML PKDD. And the idea is basically to extend random forest, this classical random forest, to streaming and make it adaptive. So what's the idea? The idea is, remember, random forest is a combination of bagging and random trees. Trees that instead of using all the attributes, each node is only going to use a random random number of attributes. So for example, we have 100 attributes. We are going to use the root square of 100, that is 10. So we are only going to select randomly 10 attributes at each node. And we are going to split using only these 10 attributes. So yeah, it's very simple. So it's only a combination of bagging and random trees. So how we can have this, how can we have an adaptive version of random forests in streaming? So basically we need streaming bagging. In this case, we use leveraging bagging. And then we need decision trees that are streaming. In this case, so we deal with random housing trees that have these properties of, again, of using these random subsets at the nodes. And one of the nice things of using bagging is that all the trees are parallel, are independent, so we can train in parallel. And finally, how to make it adaptive. So how this adaptive random forest is able to adapt to changes. So the idea is to have two detectors, one to detect a drift and one to detect one warning. So the idea is once the warning is detected, then in the background, there is a new tree that starts to grow. And when we get to the drift, then this tree that we were building on the background is going to be going to replace the old tree. So this is how, doing this, we have this adaptive random forest. So how we can improve this random forest? So one of the things is that this idea of combining bagging and random subspaces or random features, selecting random features, is quite nice, but it's really built on inside the trees. No? So it could be nice to be able to use this idea also in any type of classifier, not only on decision trees. So this is why we work on this algorithm that is called random patches. So the idea is basically combine bagging with random subspaces. And so instead of selecting the features at the node of each tree, we're going to select the attributes randomly at the root node and for all the classifier. And the nice thing then is that we can apply this to any classifier, not only to decision trees. So this is streaming random patches. This is a work that we presented last year at ICDM. And as you can see, basically what we do is in bagging, we decide not to use all the instances, and using random subspaces, we decide not to use all the features. So yeah, this is something that works quite well, and I think that currently is the state of the art and is the one that was able to beat all the other streaming classifiers as adaptive random forest, Gaussian bagging, and all the others. Okay, so another method that is quite popular in streaming is SAM-KNN. So this is a method that won the best paper award at ICDM 2016. So the idea was to have a self-adjusting memory KNN. The idea is that it keeps two memories, one short-term memory and one long-term memory. The short-term memory is basically a sliding window, and the long-term, what it's doing is that it keeps some representative of the data. So yeah, basically using clustering is able to keep some examples that represent everything that has been arriving to the stream. And then, yeah, to make the predictions, we use the best of these two memories. So yes, in this case, this year at IGCNN, we presented an ensemble version of that. And yeah, that was able to be also able to handle concept brief, and also at the same time to be able to handle this, to be able to be an ensemble method that make it much more powerful. So another setting that we are working right now is what is called delayed labeling. So this is a work that we presented last month, September, at ECML PKDD. Is this idea that in many settings, labels do not arrive at the same time that we make the prediction. So yeah, basically, so for example, in this plot, we see that, yeah, the blue instance, we've got the input data, we get the data to make the prediction, we make the prediction, but the true label is going to arrive with a delay. And this is a very realistic setting. So in this work, we presented a method for evaluating this, in the sense that what we do is that we present a measure that is going to consider how good we are doing making the predictions from the moment that the input data arrives and the label arrives. So we use all the predictions that we do from the moment that we make the first prediction until we get the final label. And finally, just two works that we're presenting this month in Discovery Science. No, sorry, this one is a work that we presented also at IGCNN this year. This is a version of XGBoost, also for evolving data streams and adaptive. And the idea is that in XGBoost, we build this ensemble. The idea is adapt XGBoost in streaming, building first ensemble, and then every time a new batch of instances arrive, what we do is that we replace one of the members of the ensemble. So doing this, we can adapt XGBoost for evolving data streams, but at the same time, we are mainly extending XGBoost as we are using all the technical tricks that XGBoost is using inside. And yeah, now finally, these two papers that are going to be presented this month in Discovery Science. So we have this new, HOEFFDING adaptive tree that is based on the idea of fairness. So as you may know, one of the problems in machine learning is that sometimes data is biased, and then the learners are biased. So yeah, in this case, what we do is that, we present an adaptation to the HOEFFDING adaptive tree so that we can consider this fairness. So basically, the idea is instead of using the information gain when we make a split, the idea is to use a combination of this information gain with fairness enhancing gain that is based on the difference between discrimination. So the idea is that if we do a split, we look at the difference between the discrimination at the beginning and discrimination once we do the split. And also the idea then is to minimize and to optimize for this new measure that combines information gain and this fairness enhancing measure. And finally, also in discovery science, we are going to present this work on unsupervised concept drift detection. So what happens when we don't have labels? There are several techniques, but in this case, what we propose is that, okay, what we can do is that we can have two models, one that we're going to call the teacher and another one that we are going to call the student. The student is going to mimic the behavior of the teacher. And then what we are going to do is that we are going to be looking at this student model, and we're going to see if this student model is having a concept drift. So we are going to assume that we have the label of the teacher as the true value, and we're going to monitor the student as a standard classifier, and basically we can use again the standard concept drift detection methods for classification. We can also use that in this case. Okay, and then just to finish, let me introduce some of the open source tools that we already have for machine learning for data streams. So let me start with MOA. So MOA is a machine learning library for mining data streams, for doing machine learning on data streams. Is in Java. It was started at University of Waikato. That's in the same group that did Weka. And it has many different methods: classification, regression, clustering, outlier detection, frequent pattern mining. And it was a project that was started at Waikato, but it had many collaborations. For example, clustering that was made by the group of Thomas Seidel in Aachen. And it's maybe right now still the most popular software for mining data streams. So if you are more interested on that, we have this book that is called Machine Learning for Data Streams with Practical Examples in MOA. This is a book that we published at MIT Press and is open available, so you don't need to buy it. You can read it online. We have a new open source tool that is called Scikit-Multiflow, that this is in Python. As you know, Python is becoming very popular, and especially because it can be used with Jupyter notebooks. So we have this software, this new software that is called Scikit-Multiflow, that is inspired in MOA and Mecha, but you can use that inside the Python ecosystem. As you can see, it's really similar to MOA. So the idea is, again, to have streams, to have learners, and then to have evaluations that we use to evaluate. And then again, remember that in streaming, we're not going to have only one value of accuracy. We're given a data set, in the standard setting, given a data set, we can get one value that is going to give the accuracy. In streaming, what we are going to have is a time series. So we are going to see how the accuracy evolves over time. And this is quite important. This is something that is in MOA, and also this is something that is in Scikit-Multiflow, where we can monitor how the accuracy, the error is monitoring, is changing, and if there is any concept drift that appears. We have another software that is called streamDM, SIM++, and here the basic idea is that is really similar to MOA, but implemented in C++. So and finally, when we are dealing with big data, then basically we need to combine streaming and distributed to be able to deal with these large big data streams. So we have this project that is called Apache SAMOA. This is a project that was started at Yahoo Labs. And the idea is to be able to use the stream engines that are in the Hadoop ecosystem, like Storm or Apache Flink. And The idea is that there is a high-level API where we can implement our classification, clustering, frequent pattern mining methods. Then we deployed this in SAMOA, and then we can decide which stream engine we want to use. That could be Storm, Flink. The nice thing is that we don't need to rewrite the code because we wrote the code with this high-level API of SAMOA, and then we can deploy in any of these. Still, you know that maybe the most popular big data software is Spark. So yeah, we have also a project that is called streamDM. This is a project for machine learning for data streams using a Spark streaming. And this is a project that is written in Scala, and also it contains the implementation of these popular methods in machine learning for data streams. So yeah, I think that this is everything that I wanted to talk. So basically, yes, just to mention that yeah, adaptive machine learning is something that is very, very important. We saw this during the pandemic that many companies needed to adapt the models and see how to use this, because yeah, it was really something needed, and we are very happy that yeah, we have already this technology that can help in these situations. So yeah, thank you very much.
Thank you very much, Albert. Very rich content and inspiring methods. So I think it's time for some questions. And I propose that the audience who are interested in raising questions simply type in the chat some Q or something so I can follow yeah, in the order of questions. I can ask them to raise their questions. So I think everyone is able to type something in the chat. Okay, let me kick off actually with oh, there is already a question from Florian. Yeah, please.
Yeah. Hi, Albert. Very nice presentation. I like it very much. And I also really like ADWIN because I use it a lot of times before. Marwan already knows because we did it in my master thesis. My question is, when you use ADWIN as an expert, as you are, we had the problem that in times where we don't have any anomaly or any drift, the window keeps growing, and we set a parameter saying, okay, we just have a window size of n. Do you have a recommendation of how to treat these long periods where no concept drifts occur, and what to do with the window size?
Oh, thanks. Yeah, that's a very good question. So I haven't thought about that, because usually as it uses logarithmic memory, yeah, the problem is not really big, but it's true that if there is no change, then yeah, this is going to grow, and maybe in this case it's really is not needed. No? So I think that yeah, maybe I think maybe the simplest way is to remove maybe old data and then say that we have like a maximum value of the size of the sliding window, and then once we reach to this size, we discard everything that, because we are really not going to need that. So maybe that's the simplest solution. I was thinking in maybe another more complex could be that if we think that there is no change, we don't update ADWIN. So we keep without new data arriving, because we know for sure that, but then yeah, in this case, the problem is that we are not going to detect change. So yeah, it's still good that we receive data. So yeah, I think that maybe the best option in this case is to decide what is the maximum size, and then once this maximum size is reached, when we remove the oldest thing. So at least we know what's the, yeah, let's keep that as a constant size for the.
Okay, thank you. Yeah, well, in practical scenarios, there will be a drift somehow, and then it will be cut down.
Yeah, that's going to happen. Oh, yeah,
Sure.
yeah, so that's going to be useful. Yeah.
Yeah, thank you very much.
Thanks.
Further questions? Yeah, I see a question from Thomas. I think you can, please, Thomas.
Yeah, thanks, Albert, for the talk. Very inspiring, as Marwan already said. In process mining, we don't have just numerical values. We have complex objects. Even a single step, a single event is a complex value. A trace for a case is even more complex. So are there the ADWIN, for example, or many others rely on a notion of average, say a sum or something.
Yeah.
If you don't have numerical values, can you substitute the average with any other aggregate? Say the median is not a good idea since it is holistic, which is available for ordered data, not necessarily numeric. What is needed? Do we have to numerize the data to make it numerical by embedding techniques, or is there another way out?
Yeah, that's quite interesting. So, yeah, at the moment, yeah, what I've seen is that all of these methods, they work with numeric values, so that they suppose that that's going to be converted to numbers. In the case that, my feeling is that if we are really interested in another type of measure, then we really need to change maybe ADWIN or extend ADWIN, or extend one of these change detectors using these other measures. But my feeling is that it's not going to be straightforward. So maybe there's going to be needed some research to see how to do that, because one of the things that we really want to still keep a small amount of memory, to use a small amount of memory. So then this is really, really quite important when we aggregate this information. So we do that, with guarantees. So in this case, I think that, maybe the main solution could be to try to extend these change detectors using to this more complex type of data, looking at how to combine them. Or I can imagine that we need to look, for example, instead of looking at the difference between the average, in this case we need to change that to look at the difference, and then we need to see how, instead of keeping the average of these sub windows, we keep these other measures. So I think maybe there is some work there, but I think it should be possible. But maybe it's not straightforward. Maybe it requires some research.
Okay. So lots of opportunities as well.
Yes, exactly. Yes. Yeah. Thanks.
Yeah. Thanks.
I see a question from Ahmed. I think you can ask it yourself, Ahmed.
Okay, thank you, Albert, for your talk. So my question is that about drift detection. I believe that it depends on monitoring the error in the classifier for the predicted label for the received item. So what if this label is not known, or let's say not known in a reasonable time, the true label? So would it still be possible to detect drifts by just looking at the features, just the values of the X vector, or the vector of features, not just for the label?
Thanks.
Thank you.
Thank you. That's a very good question. So the thing is that these traditional change detectors, they suppose that we have a classifier with all the labels, and then from there we learn. We look at the error, and then we see what there is a concept with. So in the case that we are dealing with unlabeled data, then we really need to look at not the error. We need to look at other things, and then in this case, looking, for example, at the features, how they change, how they evolve. So this is a good approach. Maybe there could be other change detection techniques based on clustering, or looking at how the data is distributed. Yeah, that's the problem of this more realistic setting. That what is happening is that, yeah, we don't have access to the labels, so maybe the labels are going to arrive with delay, and then we are really more in this semi-supervised setting. So we have examples without labels that are the ones that we are doing the predictions, and then we have some of the instances that are going to, yeah, we're going to get access to the labels. No? So then I think that we have this semi-supervised setting, maybe that is more realistic. And then, yeah, in this case, yeah, using a change detector as in the supervised setting is not a good idea. And then, yeah, I can imagine that that could be a good solution. So one of the works that we have is this unsupervised change detection. So there, what we suppose is that, okay, it could be ideal to have one classifier that can make predictions continuously and as in the supervised setting, but yeah, we don't have this. So what we do is that we simulate this. How we simulate this? We simulate this having two classifiers. And then we have a classifier that is the student. This is the one that we are going to be monitoring if there is a change. And this student classifier that needs to know what's the true label. There is no true label. So then this is why it is going to use the prediction of the teacher. So this is why we are, let's say, we are simulating having labels. So we don't have labels, but we simulate with another classifier, we simulate that there are labels. And then from this, we can use the standard techniques in supervised to be able to detect changes. Yeah, so this is one approach, but yeah, there are so many. And as you said, yeah, this is something that is quite important because this is more a realistic setting.
Thank you.
Thank you. Andrea has a question. Please go on, Andrea.
Yeah, thank you very much, Albert, for your inspiring talk. It was very nice. Also with this very nice overview of many approaches. That was really, I appreciated that. And while you were presenting, I thought that one possible way of classifying, classifying the approaches is whether they are parameters free or whether they do require parameters.
Yes.
And while you were presenting, you mentioned that one of the key components of the whole, let's say, game setting of online or stream mining is that data is assumed to be changing, to evolve over time. So if we now focus on the techniques that require parameters, how do you see that we should handle the parameters configuration over time? So assuming that I set the parameters in a certain way, which is probably domain dependent, now my underlying domain is changing, my model is drifting. How can I make sure that the parameters configuration that I set for a different domain are still valid in the new setting?
Thank you. Yeah, that's really, really interesting because I think this is something that is very, very important. And I think that, yeah, basically this is like a AutoML for streaming. No? So really is, we really want a way to monitor parameters in an automatic way, no? So that we don't need an expert user that needs to select. And especially in streaming, yeah, thing changes. So that could be really, really a mess. And then it could be nice to have methods that are able to do that. No? So I think this is something that there hasn't been many research until now, but yeah, I see that now, maybe in the last 2 years, that are starting to appear some works on that. And I think that's really, really an important problem because especially in the streaming setting is quite challenging, no? Because yeah, the data is arriving and we cannot say, okay, now stop. Now we are going to run parameters, we are going to run experiments, and after some hours, we are going to know what are the current parameters. No, we cannot do that because the stream is arriving and we need to do that incrementally. We need to do these selections and decide what are the best parameters online. And this is something that is really, really challenging. And I think that is something that is not solved. And I think that this is something that in the next years, we're going to see many, many works trying to establish this, because it's really, really important. And it's quite difficult because at the end, yeah, okay, so you are going to have a set of candidates, parameters that you would like to try. And then you need to try and select what are the best. But this is, again, you want to do that using the less amount of resources, no, less amount of time and memory. So it's quite challenging. But again, I think this is really, really important, and this is something that yeah, we should see progress in the next years. Yeah.
Okay, thank you very much. I'm happy to hear that there's room for research in there.
Yes.
Thank you.
Thank you.
Okay, so I'm looking at time. I still have one question. Maybe you have one quick answer to it. So I like the explanation about the unsupervised concept-driven detection using the teacher and the student models. Now I'm going back a bit to SAM-KNN Ensemble. So in there, you are comparing the results from both like short-term memory and long-term memory models. Can you comment a bit on that and compare it a bit to the solution in the teacher-student settings?
Okay, so yeah, this KNN, yeah. So the idea is to to simulate the idea of having a short-term memory. This is data that is arriving recently, and then what is more long-term memory. And then in this long-term memory, basically, again, is this idea of compressing, of getting what's we don't want to store all the data. So what we want is to store a small subset that is going to represent this data. So then, yeah, how we do this? So basically, we are going to use data from this sliding window. Once this data from this sliding window from the short-term memory disappears, it's going to go to this long-term memory that then is going to use this data in a more slow way. I think in this case, using clustering or to try to summarize, to try to compress, to get what's the most representative examples that can summarize all the data in this long term. And then once we need to make the predictions, then it's really simple. So it's taking examples from the two windows and then looking the nearest neighbors between the two. So it's quite a simple approach, but yeah, it seems that it's working quite well. The main, not problem, but the main issue is the speed. So it's a method that is quite really good, but as it's doing all of these things, maybe it's slower than other methods. And in streaming, speed is really important. And yeah, this is the main drawback of this method. But yeah, again, it's really good, and I think it's a good improvement over the standard KNN method.
Great. Then thank you very much for answering my question, and also for the whole keynote and answering the other questions. It was very inspiring. Thank you again for joining us at this late time there in New Zealand.